One chiral Q or D molecule can access 4 isolatable supramolecular states without changing its chemistry. Simple helices assemble with neighboring helices to create a higher-order superhelix. Temperature, cooling rate, and sonication select 4 preparation routes, producing aggregates A through D from the same molecular scaffold. Their circular dichroism spectra act as optical fingerprints, revealing distinct helicity and long-range excitonic coupling. Calorimetry maps a connected but nonlinear enthalpy landscape. From the monomer, 2 competing pathways first reach the primary helices B and C, and only then the higher-order superhelices A and D. Time exposes the kinetic asymmetry. Aggregate A reorganizes into B and C after 26 days, but it does not convert spontaneously into D. B and C remain closely connected, while C directly feeds the formation of D. Cross-seeding makes that directionality explicit. B seeds accelerate the conversion of C toward D by about 27-fold. 50% converts within 24 hours, compared with roughly 30% after 14 days without seeds. In the reverse experiment, less than 1% C seed drives more than 99% conversion of B to D within 24 hours. Finally, thermal cycling and sonication access interconversions that do not occur spontaneously or through cross-seeding. Slow cooling yields B and sonication converts B to C. Controlled sonication of D produces C at low temperature or B at higher temperature, revealing a close energetic basin separated by kinetic barriers. Together, the 4 states span 2 hierarchical levels. A and D are superhelices, while B and C are primary helices. Temperature, mechanical input, and seeding program which pathway the same molecular scaffold follows.